Hi everyone and welcome to OGLDEV. My name is Etay Meiri. I've mentioned the fixed function pipeline and the programmable pipeline a few times over the course of this series. They represent two major generations in the architecture of both the OpenGL and the GPUs. When OpenGL came out in 1992, it featured the fixed function pipeline. Version 2.0, which came out in 2004, introduced programmable shaders for the very first time. And since version 3.0, the fixed function pipeline is slowly being deprecated. Let's take a look at both of these pipelines and see how to use shaders in our games and applications. The common part between the fixed function pipeline and the programmable pipeline is, of course, the concept of a pipeline. But what exactly is the pipeline? Well, you can think of the pipeline as if it was an assembly line in a factory. In a factory, we have raw material coming in from one side. This is the input to the line. As the material goes through the line, it passes several stations. Each station has a specific task that usually transforms the material in some way. At the end of the line, we get the finished product. The fixed function pipeline is very similar in principle. The vertices and their attributes such as position, texture, coordinates, etc. represent the raw material. They pass stations such as primitive processing and primitive assembly, which work together in order to build triangles from them. Transform and light perform exactly as it sounds. They transform their position from the local coordinate space to the view coordinate space. We will go into much details on this topic in a future video. They also calculate lighting effects on them. The rasterizer is already familiar to us. It identifies the pixels that are enclosed inside each triangle. I don't want to get into too much details about the fixed function pipeline because for all practical purposes it is mostly dead. You should target the programmable pipeline and shaders in your applications and games, and this is the focus of this series. What is important to understand here is that these stations are fixed and there's not a lot of room for flexibility here. Sure, you can turn on and off some functions and you can configure some states in some stations, such as transformation matrices and lighting parameters in the transform and light stage, but you can't control the lighting equations themselves. They are built directly into the hardware. The fixed function pipeline evolved over several years, and the OpenGL as well as DirectX specifications evolved with it, but eventually developers felt restricted by the hardware. They could of course innovate somewhat within its boundaries, but at the end of the day, they were limited by what the hardware was specifically designed to do. People came up with new lighting models and new techniques that could simply not be implemented using the fixed function pipeline. Such techniques had to be implemented using a software pipeline, since software is the most flexible thing we have. However, a software pipeline has its shortcomings, most notably performance. The whole idea behind the GPU is to scale up the performance of what was previously been done on the CPU. The solution therefore was straightforward. Integrate programmable stages into the pipeline that will allow the developers to write programs to manipulate the core building blocks of vertices, primitives, and pixels and break free of the limitations of fixed function hardware. These programs are known as shaders. Let's take a look at a diagram of the programmable pipeline. You can see that even the programmable pipeline is composed of a combination of fixed function and programmable units. We enter the pipeline from the vertex specification stage. This is the corresponding stage to the vertex processing and assembly stages in the fixed function pipeline. It understands the layout of vertex attributes in vertex buffers and knows how to build the basic primitives such as points, lines, and triangles. Next, we encounter our first programmable unit, the vertex shader. The vertex shader is executed once on every input vertex. It receives the original vertex attributes and enables the current vertex shader program to manipulate every one of these attributes freely. The classic job of the vertex shader is still to transform the vertex position to the view coordinate system and in some cases handle part of the lighting model, but these must now be implemented in shader code. Shaders in OpenGL are written in GLSL, the OpenGL shading language. This language is highly expressive and contains classic constructs such as conditionals, loops, and functions, as well as more 3D-oriented mechanisms such as vector and matrix math. There is almost no limit to what you can write in GLSL, and it provides full control over all the attributes of every vertex as well as the color of every pixel. Indeed, even the vertex input attributes became much more flexible. In the fixed function pipeline, you could only use the predefined attributes, whereas in the programmable pipeline, you can add user-specified attributes that the system passes to your shader where they are used for your amazing lighting effect. I like to imagine the first two stages of the pipeline, the vertex specification and the vertex shader, as a big for loop that traverses the vertex buffer and executes the vertex shader on every vertex. Sounds like a lot of work, doesn't it? For this reason, all the shading units are implemented using a small CPU core called a shading unit. GPU vendors like to brag about the number of shading cores in their products, and the amazing speed of the GPU comes from the fact that it is capable of spreading the shading work over hundreds or more shading units and run them in parallel on multiple vertices and pixels. The next stage in the pipeline is the tessellation unit. This is a relatively new addition to the pipeline, and I don't want to get into too much details at this point because we're going to have a few dedicated videos just for this topic. In a nutshell, this unit has two shading substages of its own, and it helps implement smooth surfaces such as Bezier surfaces. This unit is optional, and we will keep it disabled until we are ready to turn it on. The next stage is also optional and was not present when the original programmable pipeline was conceived. While the vertex shader is limited to the scope of a single vertex, the geometry shader can see the entire triangle as well as its three neighbors. This enables techniques such as shadow volumes, since one of the unique properties of this stage is the ability to create new geometry. While the vertex shader always takes one vertex as input and outputs a single vertex, the geometry shader can generate new primitives. We will keep this stage disabled as well until we get to the first technique that uses it. After the geometry shader comes our good old rasterizer. Not much has changed in this fixed function unit, so we can continue to the fragment shader. This programmable stage works in tight integration with the rasterizer. The rasterizer identifies the pixels in every triangle and then executes the fragment shader on every pixel. The screen space position of the pixel has already been determined at this stage, so the main job of the fragment shader is to set its color. Many interesting lighting and shadowing techniques are implemented in this stage. Now that we have seen an overview of the programmable pipeline, let's review the practical stages that we must take in order to drive it. The first thing we need to do is to allocate a program handle. Shaders in OpenGL are not set individually into their respective shader stages in the pipeline. Instead, they are linked together in a way which is similar to the way in which object files in C++ are linked into an executable. When the program becomes active in the pipeline, its shaders are also enabled in their shader stages. The handle is just an identifier for the program in the same way that file descriptors provide access to files. Next, we allocate a handle for each shader that we plan to include in the program. Again, the handle is an identifier for the shader that we are going to compile. We need to get the shader source in GLSL from somewhere. A straightforward approach will be to save such sources in text files. This allows us to edit them offline and then rerun our GL application to see the effect. You can even include the sources directly into regular strings in your C++ application, but this means that the application must be compiled on every change in the shader. Now we can load the source into the shader and compile it. The OpenGL driver will execute its internal compiler in order to translate the GLSL code into machine-specific instructions that match the current GPU. GPU vendors have an opportunity here to include special optimizations for their hardware in the GLSL compiler. Next, we attach the compiled shader to the program. We repeat this process for every shader that we plan to include in the program. we link the program. The shader compiler now has a chance to perform cross-shader optimizations. The program is now ready, and we can enable it in the pipeline. There can only be one enabled program at any given moment. At this point, the driver loads the shaders inside the program into their respective stages. On the next draw command, these shaders will be used to process the vertices, primitives, and pixels. We must repeat the entire process for every shader combination that we plan to use. Since compilation can take some time, most applications and games have a bring-up phase where all the shaders are created, compiled, and linked, so that when the real action starts, the shaders are ready to be used. Now let's see the required changes in the code. In the main function, I've added a call to compile shaders. This function encapsulates the process that we have just reviewed. We start by calling GLCreateProgram in order to allocate a handle for our program. The system may run out of resources, so it's important that we check that we are getting a non-zero handle. Next, we call readFile with the name of the shader text file and an std string object which will be populated with the contents of that file. Note that for simplicity, the names of the two shader files are included here in the global section. Let's quickly review the implementation of readFile, which is declared in OGLDEV_util.h in the include directory and defined in OGLDEV_util.cpp in the common directory. I didn't include OGLDEV_util.h here explicitly because OGLDEV Math 3D already includes it. Here's the declaration and the implementation. The implementation is very simple. We open the file for reading using ifstream, and if there was no error here, we read the file line by line using the standard getLine function. Each line that we read is appended to the second parameter to the function. Note that we must also append a new line because it is not included in the output of getLine. You don't have to use the standard C++ library to do that. You can also use regular C functions such as fopen or open. When we are finished, we close the file and return true to indicate that there was no error. When we are back to the compile shaders function, we have a string with the entire contents of the shader. We call the local function addShader and provided the program handle, the contents of the shader string, and an enum, which is defined by the OpenGL spec to indicate the type of the shader. Here, we are using GL vertex shader and GL fragment shader. The OpenGL spec includes additional enums for the other shader stages. addShader wraps several common actions for all shader types. Let's review it. First, we create a shader handle by calling GLCreateShader. Next, we call GLShaderSource in order to load the shader text into the shader handle. This function takes 4 parameters. The first one is the shader handle that we have just allocated. The last 2 are pointers to an array of string pointers and an array of length, respectively. The second parameter is the number of elements in each of these 2 arrays. This allows you to break your shader into multiple strings by having the array of string pointers point to each shader string and placing the lengths of each string in the corresponding location in the array of length. We don't need this kind of flexibility, so our array of string pointers and array of length have a single element. We set that single element in the array of string pointers to point to the shader text we got as the second parameter to this function. And we set the length of this text in the single element of the length array. We can now compile the program by calling GLCompileShader on the shader handle. We will most likely spend a lot of time fixing shader problems, so it is imperative that we check for compilation errors. We do this by calling glGetShaderIV on the shader handle. This is a generic function for querying stuff from the shader object. we are querying for compilation status by having glCompile status as the second parameter and the address of an integer for the result. If the result is 0, we call glShaderInfoLog with the shader handle, the length of an array of characters, and the address of that array in the last parameter. The third parameter is optional and can be used if you're interested in the number of characters actually returned. We don't care about it, so we have null here. We print the error string and exit in this case. If there was no error, we call GLAttachShader using the program handle and the shader handle to connect the shader to our program. We can now go back to the compile shaders function, load the source for the fragment shader, and use addShader again to compile and attach it. With both vertex and fragment shader compiled and attached to our program, we can go ahead and link the program by calling GLLinkProgram with the program handle as the parameter. It's critical to check for link errors, so we use GLGetProgramIV, the program counterpart of GLGetShaderIV, which we saw earlier. Here we use GLLinkStatus as the action enum. The rest is very similar, so let's skip it. Before using the linked program, you should make sure it is compatible with the current state of the OpenGL runtime. Sometimes a program that has been successfully linked turns out not to be compatible with the current state, so it is a recommended good practice to call GLValidateProgram to check it. In some cases, this function can even provide hints on how to optimize the shader. I haven't actually seen such hints, but since the OpenGL spec says so, it's good to be aware of it. We get the validation status by calling GLGetProgramIV again, this time with the GLValidateStatus enum. Finally, we call GLUseProgram to make the program and its shaders active on the GPU. There's nothing more that needs to be done in the application code, so let's take a look at the shaders themselves. Remember that we have the path to the shaders right here in the source file. Let's start with shader.vs, which is the vertex shader. The file is located in the same directory as the CPP file. At the top of the shader, we have a version directive, which is specified as #version and then the version number. GLSL has a specification of its own, and each revision of the spec has a version attached to it. We must tell the compiler which version to target because some language features may require newer versions, and each driver supports up to a certain version and may not be compatible with all the previous revisions. We can see a table that matches OpenGL versions with GLSL versions in the Wikipedia page of GLSL. The last column shows how to write the version number in the shader. We can see that the last version is 4.60.5. In our shader, I'm using a slightly older version, 3.3, because I'm not using any new features here and to make sure that many people can run this out of the box. In the future, we may use newer versions. After the version comes the profile argument, which can be compatibility, core, or ES. OpenGL includes a compatibility spec with older features that are slowly being deprecated. We don't want to go there, so we use core. ES is for mobile devices, but we target OpenGL on the desktop, so we don't need it. Next, we specify the single attribute that goes into the shader. Remember that the vertex shader is always executed on a single input vertex, and it must output a single vertex, no more and no less. The shader is going to manipulate the attributes of the input vertex, so it must declare what attributes it expects to receive. This declaration is a bit complex, so let's break it into pieces. The last token is the name of the attribute. This is the same as the C language, where the name of a variable comes after its type. Same as C, the type of the attribute comes just before it. In this case, we have a vector of 3 floating points, and the name of this type in GLSL is simply vec3. We will also omit vec2 and vec4 and a bunch of other types. Since vectors are considered core building blocks in 3D, they have their own native types, so you don't need to create vectors yourself. Before the attribute type, we have the storage qualifier. This tells the compiler whether this attribute is input or output. There are also other qualifiers, such as uniforms for constant data, which we will meet in the next tutorial. In the case of input attributes, you have the option to specify all the vertex attributes that are in the buffer or just a subset of them. In the case of output attributes, you can even create new attributes based on calculations inside your shader. The first half of the declaration is a bit tricky. We have to bind this GLSL attribute to a variable in a buffer in our C++ application. In the CPP file, we have a call to GLVertexAttrib pointer, which tells OpenGL the layout of the vertex in the buffer. This call also specifies that the attribute is on index 0. We want to bind it to the position attribute in the shader, so we specify layout and location 0 in parentheses. Such explicit binding is the simplest thing to do, so it's okay at this stage. In a real-world application, you may prefer to keep your shaders more generic by not including the layout identifier. This will allow you to use the same shader with different applications without enforcing these applications to use the same index. We can do this by querying the index from the compiled shader and using that index in GLVertexAttrib pointer instead of the hard-coded index. Next comes the shader main function, which is very similar to the main function in C. Every shader must include one such function, even if your shader is created out of multiple GLSL files. Note that main takes no input parameters and returns nothing. This is because we are using the in and out storage qualifiers in the attributes declarations. The vertex shader generates a vec4 output by multiplying the x and y components of the position attribute by half. This will create a smaller triangle in comparison to the triangle from the previous episode. There are a couple of things we need to note here. We are outputting a vec4 and not vec3. In the last component, we have a hard-coded 1. This is required because of the way the rasterizer operates, and it will become clear when we start talking about projection. For now, simply make sure to have 1 in the last component of your position vector. In addition, the output goes into the special system variable GL_position. This special variable must not be declared as output explicitly. It makes the life of the rasterizer simpler because you may be outputting several attributes and the rasterizer must be told which attribute is the one that actually controls the position of the triangle. The rasterizer only has to look in that special variable to do that. This completes our vertex shader. Now let's take a look at the fragment shader, which is in shader.fs. We begin with the same version declaration as in the vertex shader. Next, we declare our single output variable, which is the color of this pixel. Remember that when the fragment shader is called, the rasterizer has already identified the pixels that are inside this triangle, and it calls the fragment shader for each pixel to determine its color. Since we have just a single output variable, the rasterizer will assume that it contains the output color. You can have multiple output variables from a fragment shader, but in this case you will need to explicitly specify which one contains the color. We declare frag color as vec4 to match our RGBA window, which we specified in the call to glot_init display mode. The fragment shader has its own main function. Here, we write the red color to the output variable frag color. We are now ready to build and run the code. So now we have the infrastructure ready and we can start using shaders. I hope you enjoyed this episode and found it useful. Let me know what you think in the comments. In the next video, we will learn how to use uniforms. They represent constant shader data, such as matrices. Thank you for watching, and I will see you soon.